Hello, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements, and welcome to the next video in our FEA101 series, which is an introduction to finite element analysis. And today we'll be going to look on the constant strain triangle, which is the first two-dimensional element we're going to consider on this short little course. So let's just talk quickly about 2D plane elements. So plane stress and plane strain elements will have the same formulation. In other words, they'll have the same shape functions, matrices, and strain displacement matrices, but the material property matrix D will be different. So for example, some examples of plane stress applications are anything where the model is very thin coming out of the screen. So things like a thin plate with a hole under tension, a very thin cantilever beam, or analysis of a wrench. So in all of these cases, the thickness coming out of the screen is very small. And plane strain then is almost the opposite of that. It's when we're looking at something where the thickness coming out of the screen would be very large. So take for example this pressure vessel here. If we took a slice through that pressure vessel and modeled 1/4 of that slice, our plane strain model would assume that the thickness out of the screen here is very large. And same with the spline shaft, and the example of a dam is often used as well for these. So plane stress, very thin, very little thickness out of the screen. Plane strain, significant thickness out of the screen. As their name suggests, this one here then has zero stress coming out of the screen, but not zero strain. And this one here has zero strain. In other words, it's not going to change its length in the thickness direction, but it is allowed to have stress in that direction. Okay, so we've talked about these previously, so they're back in chapter 2 of the book and also video number 3 of this series. We went through what plane stress and plane strain are. So again, plane stress, we can have stress in the x and y directions here, but no stress in the z direction. But we are allowed to have strain in the z direction, so that means it can change its thickness in the z direction. And this then is the equation that defines plane stress. And then again, plane strain being almost the opposite to that. Again, we have stress in the x and y direction, but this time the stress in the z direction is non-zero, but we can't have any strain in the z direction. So effectively what we're saying is that the thickness in the z direction is so large that any strain would be insignificant there. Okay, and then that's our equation for plane strain. Okay, so again, we've got stress in the x, y, and a shear stress between those two directions, and strain in the x and y and a shear strain between those two directions. And that's the same in both cases. It's just the bit in the middle, the D matrix, which relates stress to strain, is different depending on whether you're using plane stress or plane strain. So in both cases, we can have, whether they're plane stress or plane strain, we essentially have 4 types of elements that are used in most common FEA software, and we can have linear triangles and rectangles, and we can have quadratic triangles and rectangles. So the one we're dealing with here in this video is called a constant strain triangle. It's a 3-node triangle with straight edges. You can also have a linear strain triangle, which is a 6-node triangle with curved edges. You can have a bilinear quadrilateral, which is also known as a Q4, which has got 4 nodes and straight edges in between those. And finally, we can have quadratic quadrilaterals, or Q8 elements, which have 8 nodes and curved edges in between those nodes. So as I said, this video is focused on the constant strain triangle, which is the most simple of the 2D elements. We have 3 nodes and we have straight edges in between those 3 nodes. So if we go ahead and take a look at the element in a bit more detail now. So we've got 3 nodes. We normally designate those nodes I, J, and K. And each node will have an x and a y coordinate in our global coordinate system. So, for example, the coordinate of node I is xi and yi. Coordinate of node j is xj and yj, and so on. And then each node is allowed to move in the x and y direction. So it'll have a displacement ui in the x direction and vi in the y direction for node I, and similarly we'd have uj and vj for node j, and uk and vk for node k. 3 nodes, straight edges in between those nodes. So 3 nodes, I, j, and k. 2 degrees of freedom at each node. In other words, each node can move in the u and the v direction. Straight edges between the nodes, And the ideal shape is an equilateral triangle. Okay, so that would be our ideal shape for the element. And the equations are built on the element having that shape. So the further we go from that shape, the less reliable the results will be using this element. Because we have three nodes, then that implies that we have three shape functions, Si, Sj, and Sk. We're going to use linear functions here, which is why the element is known as the constant strain triangle. Because if we have linear shape functions, that implies a constant strain within the element and also constant stress within the element. And we'll come back and talk about that a little bit later on. So the first thing we need to talk about is iso-parametric mapping. So we want to define our element in our usual coordinates eta and neta and be able to relate those coordinates then into the xy space. So again, our ultimate goal here is to be able to determine the stiffness matrix for the element in as simple a manner as possible. So we're going to follow our usual method of using the isoparametric mapping. Our stiffness matrix then will, as always, be of the form BdB, where B is the strain displacement equations, D is the material property matrix, which will be set by whether we use plane stress or plane strain. So once we know B and we know D, we can effectively form our stiffness matrix. Strain displacement matrix, which is what we're basically, our first step is to find that so we can form our K, is going to be a function of ds dx and ds dy. So in other words, before in the previous elements we looked at, we only had one dimension. Our strain displacement matrix would have really just been a function of ds dx. So it would have been the partial differentiation of the shape functions in the x direction. But now we have to differentiate the shape functions in two directions, so it becomes a little bit more complicated. So as usual then, we can, if we know our shape functions si, sj and sk, and we know the displacement of the nodes I, j and k, we can find the displacement at any other point within the element. So that's what these two equations here are saying. They're saying, well, that the x displacement is a function of the shape functions times the x displacement of each of the nodes, and the same with the y displacement. So in order then to form our element equations, we're going to start off by considering the three-node element in isoparametric space. We make the triangle a right-angled triangle, which allows us to easily define the shape functions. So here we put node I at the coordinates 1 and 0, so it's got eta of 1 and neta of 0. J has coordinates eta 0 and neta 1, and K has the coordinates 0, 0. So what we're trying to do now is map a point on our template element into a point in physical space in the xy space. So again, that's our mapping here. We're taking that point in eta neta space and mapping it over to xy space. So x will be a function of eta and neta, and y will also be a function of eta and neta. So then we can find the coordinate of any point once we know the shape functions and we know the coordinates of the three nodes. So if you look at these two equations here, they're of the same form. So we have x is equal to si xi plus sj xj plus sk xk, and again the same replacing x with u. We still have the same format here. So the fact that we're using the same shape functions to do the mapping and also to interpolate displacement within the element means we're using an isoparametric formulation. So if we take a look at our element in eta neta space, we can see that we have node I is at eta equal to 1, node j is at neta equal to 1. And let's just try and form the shape function. So let's consider si. It must have a value of 1 at node I and a value of 0 at the other nodes j and k. So the way we've set this up makes it really simple. We can essentially say that si is equal to the eta coordinate, okay? Because si being equal to 1 will give you that point there. Si being equal to 0.5 is in here somewhere. Si being equal to 0 is on that line there. So si is just equal to eta. Similarly, we have sj just being equal to neta. So sj will have a value of 1 here and have a value of 0 at the other nodes, and we'll have in between values in between. And then sk is 1 minus eta minus neta. So again, here it'll have a value of 1, here it'll have a value of 0, and here it'll have a value of 0, and it'll linearly taper down to those points. Okay, so if you look at the way we've set this up now, each shape function has a value of 1 at its own node and a value of 0 at the other nodes. So it satisfies the Kronecker delta property that we talked about before. Also, at any point within the element, si plus sj plus sk is equal to 1. And again, maybe just check this for yourself. Take a point in here somewhere that has 0.5, 0.25, and just work out what SI, SJ, and SK will be, and you'll find they'll work out to be 1. The use of the iso-parametric space, or sorry, the parametric space here, eta and neta, allows us to really easily define these shape functions. They're much more difficult to define if you try and do it in XY space, and they're not as useful. Okay, so again, and we're going to follow this procedure when we go on to more complicated 2D elements as well. We've used it already with the one-dimensional elements we looked at. So the advantage of using this isoparametric formulation is that you have the same procedure used over and over again. It's not specific to specific element types. So if we just take a look at those shape functions then, and take a look at what they're doing, if we draw out our element here, so here we have our ijk, and here we have our ijk here, there's our eta equal to 1 line, which is this one here. So I've just drawn these on a surface and said that, well, the vertical direction is magnitude of shape function. So if we look at SI has a value of 1 at node I, and it tapers down to 0 at node J and node K. So this will be the surface describing what SI looks like. Similarly, SJ has a value of 1 at node J and 0 at the others, and finally SK has a value of 1 at node K and a value of 0 at the others. So again, if we were to visualize these shape functions using the vertical direction as shape function magnitude, this is what they would look like. Okay, so we've already established we have our 3-node element in its parametric coordinates eta and neta here. We've established the shape functions here, SI, SJ, and SK. We've already talked about using our shape functions to relate specific displacement of the nodes to any displacement of any particular point. So for example, if we wanted to find the displacement of a particular point in here, once we knew its eta and neta coordinates, we can find out what the values of the shape functions are at that point. And once we put those in here and with the known displacements of the nodes, we can find the displacement at that point. So we can interpolate displacement within the element using the shape functions. This can be expressed in matrix form then. So we can say U is equal to S times U. And in this case, just expanding that out makes it look like this. So if we multiply this equation out, we get this here. Okay, this is just a matrix form of this equation here. Similarly, we can do the same thing with the coordinates and say, well, we can find the coordinate of any point once we know the shape functions at that point and once we know the coordinates of the 3 corners of the element. Okay, so we have the same type of equations. This is the isoparametric formulation again. Expanding out then those equations from the previous slide. So what I'm doing here is, instead of SI, I'm putting in eta for SI, I'm putting in neta for SJ, and I'm putting in 1 minus eta minus neta for SK. And then I expand that out and I get these equations here. Okay, so these are here expressed in shape function form. Here I've put in the shape functions which contain the natural coordinates. So now I have the natural coordinates in here, eta and neta. Similarly, I can do that for the x and y as well. And replacing u with x and v with y. And here now I have an equation that relates my global coordinate to the local coordinate. Okay, so now I have this transformation here between local and global coordinates. So all of the above equations then have the form, if you look at them, f is equal to fi minus fk eta plus fj minus fk neta plus fk. So again, f can be x or y, or it can be u or v. So if you go and check those there, you'll see they're all exactly the same. We often write these in shorthand form because we use this isoparametric relationship so much that we say that, well, fi minus fk is fik, fj minus fk is fjk. Okay, so fi minus fk is fi minus fk. So we'll use this later on just to make the equations a little bit more readable. Okay, so let's do something about what we know so far. So I've mentioned this a few times, that if you know the coordinates of a point, you can find the shape functions at that point and so on, and you can transform between coordinates. So let's take an example of this. So here we're given a constant strain triangle. So again, it's got 3 nodes, I, J, K. We're given the coordinates of the 3 nodes, and we're told there's a point P somewhere inside in the element. And this point P has the coordinates 0.25 and 0.25. And we're asked, evaluate the shape functions at P. Okay, So the first thing we're going to do is use one of those equations we just had above. And we're going to use the equation that says, well, x is equal to xi minus xk eta plus xj minus xk neta plus xk. So it's one of those iso-parametric equations. And we're going to put everything we know into that. So xi is going to be 0.1, xk is going to be 0.3, xj is going to be 0.4, and xk again is 0.3, and xk is 0.3. So we can put all those in there. And now x, the point we're concerned with, so that's going to be the x there, so that's going to be the 0.25 for the point P. Okay, so we're putting in all the information that we know into this top line here. These lines then just work our way down through. So in the end, we're left with this equation here, where we have an equation with eta and neta in it. Okay, so we haven't got enough information so far to determine the eta and neta. So we've gotten an equation with eta and neta. We'll just call that equation A. Now we're going to do the same thing for the y-coordinate. Okay, again, I'm going to use the iso-parametric equation here. And now we've got another equation with eta and neta. So we've got equation A and equation B. We can solve these together. So solving these simultaneous equations A and B gives us eta is equal to 0.357 and neta is equal to 0.214. So they are the eta and neta coordinates of that point P. So essentially what we're doing here is we've mapped backwards. We've mapped from the element in xy space and we found out the eta neta coordinates of a particular point in xy space in that element. Okay, so now that we know eta and neta, we can work out the value of the shape functions. So si is eta, sj is neta, and sk is 1 minus eta minus neta. So there are our three shape functions there. And as usual, it's always good to perform a quick check. So just checking here shows us that si plus sj plus sk is equal to 1. So our results would appear valid there. Okay, so now we're going to go ahead and start looking at how to obtain the B matrix for this element. So again, remember we already know the D matrix based on whether it's plane stress or plane strain. So if we can determine the B matrix, then we can form the stiffness matrix, and then we can formulate an FEA and go ahead and solve some problems using it. So this is just some of the information that we've already established. Our 3-node element in its natural coordinate system. We have u is equal to s times u, and we have our three shape functions. And again, we can expand out our u is equal to s times u if we like. So thinking about strain and displacement and relating strain to displacement. So the strain displacement equations for a 2D plane stress or plane strain problem are these. Okay, so we're saying strain in the x direction is du dx, strain in the y direction is dv dy, and shear strain is du dy plus dv dx. Okay, so if we look here and just take u for an example, so we have du dx. We've already said, well, we can replace u, which is displacement, a generalized displacement, with s times u, and s is the shape function matrix, and u is the vector of nodal displacements. In other words, a list of the displacements of each node in the x and y direction. So these are normally two things that we will know, or we can find out. Okay, so we'll know our shape function matrix from all this information here, and we can determine these when we solve our FEA, or we already know them if we've already solved our FEA. Okay, so now what we're going to try and do is turn this general strain displacement equation into something more usable in terms of FEA. So we can say, taking a look at this du dx, we can replace u with s times u. So we can replace du dx with dsu dx. Okay. Now the next thing to notice is, well, u is just a list of numbers. It's just a list of the displacement of each node. So for example, it could be 0.2, 0.4, 0.3, 0.7, so on. So there's nothing differentiable in terms of x in there. So we can take u out of this differentiation here and say, well, it's going to be the partial differentiation with respect to x of the shape functions times u. Okay. So if we compare this then to our strain displacement equation in FEA, so normally we have our strain is equal to strain displacement equation times the nodal displacement vector, which is this. And now we've just said, well, we have ds dx times u. It's pretty clear here that the b is going to be made up from that ds dx. Now we've only done this for one line. We've only done it for the du dx. That same thing would happen to your dv dx and also the bottom line as well. So a general way of writing this is saying, well, the B matrix is going to be a function of ds dx and ds dy. Okay, so it's going to be a function of the shape functions differentiated with respect to the x and y directions. So we need to kind of delve more into this and try and figure this out. Okay, so again, we've already established this in our previous slide. We went through there and said, well, the K matrix is going to be a function of the B matrix, and the B matrix is a function of the differentiation of the shape functions with respect to the global x and y. Now, we've got, unfortunately, have already moved into the eta-neta space, and we're defining everything in the eta-neta space. So we need to be able to kind of re-express these ds dx's and ds dy's as ds d-etas and ds d-netas, because we're already working in this space here, and we've already established our shape functions in this space. So using the chain rule, we can say, well, we can replace ds dx with ds d-eta times d-eta dx. So again, if you look at this here, if we get rid of both of those, we're left with ds dx. And we can say ds d-neta times d-neta dx. And again, the d-netas cancel out there, so we're essentially left with ds dx. So we're using the chain rule in the x and the y direction. Now, if we take a look at these differentials, the first thing we can notice, well, ds d-eta and ds d-neta are really easy to determine. I mean, ds d-eta is 1, dsj d-neta is 1, and so on. So we can differentiate these really easily with respect to eta and neta. D-eta dx, though, and d-neta dx, d-eta, those are difficult to determine. Okay, so we're differentiating the natural coordinates with respect to the global coordinates. Okay, so it's very, very difficult to determine those. So in order to get around that, let's try and rewrite this equation so that it's a bit more easy to work out what's on this side. So what we're going to do is use the chain rule on partial derivatives in natural coordinates instead. So here we're starting on this side with ds dx and ds dy. So what about if we started on this side with ds d-eta? So we're going to say ds d-eta, ds d-neta. Okay, so we're using partial derivatives in the natural coordinates as opposed to partial derivatives in the global coordinates. So now we have ds dx, and we have dx d-eta, ds dy, and dy d-eta. Okay, so let's just take a look at this. Let's go on to the next slide and take a look at this. So in the previous slide we have this. So what we're going to do now is write this in matrix form. Okay, so this is the same set of equations expressed in matrix form. So here we just have ds d-eta, ds d-neta as usual. And here, if I multiply this row into this column, I will get this. So again, dx d-eta times ds dx. So there it is there. Dx d-eta, sorry, dy d-eta times ds dy. There it is there, and so on. So I've just rewritten this in matrix form. Okay, so here now I have ds d-eta, ds d-neta. Here I have ds dx, ds dy. So I have differentials in terms of eta being related to the same differential in terms of x and y by this matrix in the middle here. So this matrix relates differentials in one space to differentials in another space. So a matrix that does that transforms from one space or one coordinate system into another, we generally call that a Jacobian matrix. Okay, so this case, this is the Jacobian matrix here. Now, remember, we were originally seeking to find out these in terms of these. Okay, but we've used a little bit of a device and that we went the other way instead. So now what we're going to do is invert that back to what we started off with again. So now we've got ds dx and ds dy back on this side again, and eta and neta on this side, and we have the inverse of that matrix there, or the inverse of the Jacobian over here. So let's evaluate the terms then inside in the Jacobian matrix. So actually, maybe just jump back quickly before we do that. Let's look at what's going in there. What does it say? Well, it says dx d-eta. In other words, how is eta varying on x? Okay, so is there something we can do with these dx d-eta, dx d-neta, dy? So let's just take a look at those. So previously we had our iso-parametric relationship. And again, this is very useful because it's relating global coordinates to local coordinates over here. So what we can do is we can evaluate the partial derivatives from the Jacobian. So let's say dx d-eta was one of them. Okay, so essentially what we can do is take x and differentiate with respect to eta, and we'll just find this bit here is the only bit that's left, xi minus xk. Again, there's no eta here, no eta here. So if we differentiate x with respect to eta, we're just left with that, which is there. Similarly with dx d neta, again, there's the neta part there. And again, same with the y direction. So we get the differentials of x with respect to eta and neta and y with respect to eta and neta are just based on the coordinates of the nodes. So remember xi and xk, yi, yk, yj, they're just the coordinates of the nodes ij and k. And we'll know the coordinates of those nodes by defining our element. So now we can rewrite our Jacobian, and instead of having these differentials, we can have really specific things in here. We can say, well, the Jacobian is now just xi minus xk, yi minus yk, and so on. And we can invert the Jacobian really easily because it's a 2 by 2 matrix. So inverting a 2 by 2 matrix, you have 1 divided by the determinant, and you swap over the rows and columns, okay, and you get this here. And again, just in case you don't remember your matrix algebra, the determinant of the matrix is going to be this multiplied by that minus this multiplied by that. Okay, so that's what this is just saying here. Again, if you don't remember what this is, maybe just go and look at some information on basic matrix algebra. One thing to notice here is that det j is twice the area of the triangle element. So in other words, area is going to be half the determinant of the Jacobian. And this is something we can use quite conveniently to calculate the area of the element whenever we need to do that. And the area of the element does form a part of the formulation of the constant strain triangle element, as we'll see when we go through this. Okay, so remember again what we're doing. Why did we get here with this inverse of the Jacobian? Because this inverse of the Jacobian relates the shape functions in xy space to the shape functions in eta space. Okay, so some comments on that Jacobian then. Well, what happens if the determinant of the Jacobian is equal to 0 or the determinant of the Jacobian is less than 0? The shape function derivatives cannot be obtained if det j is equal to 0 anywhere within the element. And thus the Jacobian is an important criterion for evaluating the validity of mapping as well as the quality of the element. Every point in the reference element eta neta should be mapped into the interior of the physical element xy, otherwise the Jacobian becomes negative. If multiple points in eta neta coordinates are mapped onto a single point in xy coordinates, the Jacobian becomes 0 at that point. So it's important to maintain the element shape so that the Jacobian is positive everywhere in the element. And in this case, it means staying as close to an equilateral triangle as possible. So I mentioned that at the start there. That's why we use the ideal shape as an equilateral triangle. So you want to avoid high aspect ratios and obtuse angles. So if you have experience of meshing two-dimensional elements in finite elements or obtaining results from an analysis using 2D elements, you may have seen an error previously where a negative Jacobian was obtained. So again, the reason for that is given here. Okay, so the element has become so poorly shaped basically that the mapping is breaking down, and we're not able to map the eta neta coordinates onto the xy coordinate. The reason for that is always a poorly shaped element, so high aspect ratio or obtuse angles. So let's go back to our B matrix again and trying to obtain it. We had a couple of words in the Jacobian there, but using the equations from the previous slides then we can form the equations for u and v. So we can say, well, du dx and du dy is the inverse of the Jacobian times du d eta du d neta. Okay, and then we put that in there and multiply it out, we get these are just our elements of the Jacobian and they're multiplied by this here. And similarly we can do the same thing for the v, dv dx and dv dy, and again we can obtain an expression here for dv dx and dv dy in terms of the coordinates of the nodes and dv d eta and dv d neta. So now what we're going to do is put those together to try and make the 2D strain displacement relations. Again, if you remember, this is what we started off with. This is the general strain displacement for a plane stress or plane strain problem. Okay, and we wanted to re-express these x's and y's in terms of eta and neta. So now, putting together the equations from the previous slide, we now have these equations here. So now each of these equations are based on the coordinates of the nodes and du d eta or du d neta, dv d eta or dv d neta. Okay, so that's all that's in there. So we're going to re-express this one in shorthand form because it's getting a little bit complicated. So let's just do that. And that's our shorthand form. So again, yj minus yk just becomes yjk. Okay, so that's our equation there. So now we have to deal with these du d-etas and du d-netas. So we're going to deal with them in the same way that we dealt with the dx d-etas and dv d-etas and so on. So now we have our displacement interpolation. Okay, so we have u is equal to siui plus sjuj plus skuk. If we put in the shape functions eta and neta, 1 minus eta and eta, we get this. Okay, so now anywhere we have du d eta or dv d neta or whatever it is, we can differentiate these to give us that. So again, here we are here. Du d eta, we differentiate this top line in terms of eta, and we get ui minus uk. dv d neta, we differentiate the bottom line here in terms of neta, and we get vj minus vk. Okay, so now we've replaced these partial differentials with equations that are literally based on the displacement of the nodes. So we can put that into our previous equation, and now we have this. Okay, so now we have our strain is going to be 1 over the determinant of the Jacobian based on all of this here, which is the coordinates of the nodes and the displacement of the nodes. So again, writing that in shorthand form gives us this here. So now we have our strain is again just the coordinates of the nodes, the displacement of the nodes, and the determinant of the Jacobian. As usual, we like to turn these things into matrices because it makes it much easier to write programs to do finite element analysis, and also much easier to deal with in general. So this equation can be written in the form E is equal to B times U, where we have B ends up being that and U is that. Okay, so if I multiply this by that, I will get this. Okay, so my strain is the B matrix, which is 1 over the determinant of the Jacobian, the various coordinates of the nodes of the element, and my U matrix is my usual U matrix, or sorry, U vector is my nodal displacement vector, which is a list of the displacement of each of the nodes. So we now have an expression for B, which is solely based on the coordinates of the 3 nodes in the constant strain triangle element. Okay, so let's look at an example of trying to obtain the B matrix for a particular element. So we have a 3-node CST finite element, which was used in a plane stress analysis problem of a flat plate. We're given the coordinates of each of the nodes, and we're given the displacement of each of the nodes after the FEA was done. So for example, here you can see, well, node I didn't move. Node J moved 2 by 10 to the minus 6 in the x direction and 0 in the y direction. That one there, it just went over this way a bit, didn't go up. And then node K, which is this one here, moved across 1 and down minus 1. Okay, so it moved over this way a little bit and down a little bit as well. Okay, so that's what that nodal displacement vector is telling us. The resultant nodal displacement vector is shown together with the initial coordinates of the nodes. Given the elastic modulus is 210 gigapascals and Poisson's ratio is 0.27, determine the stress and strain in the plate. Okay, so using equation 6.76, we have, it's basically our equation for the determinant of the Jacobian. We put in all our values there, so xi minus xk is going to be 0 minus 0.02, which is what we get there. Again, yj minus yk similarly is going to be that. So again, we can work our way through all of this, and we work out that the determinant of our Jacobian is 0.0007 meters squared. So we may now determine the B matrix from the equation we had previously. So our B matrix, again, remember, it's going to be yj minus yk. Okay, so yj minus yk, 0, yk minus yi, and so on. Okay, so if we look at the first one, yj minus yk, we've got 0.01 minus 0.03, gives me minus 0.02. Let's just take another one at random, xj minus xi, so it's going to be 0.03 minus 0, which is going to give me 0.03. Okay, so we just fit in all the values there. We know that det j is 0.0007, and so there's our B matrix for this element. So we can now determine the element strain from strain is equal to B times U. So there's our B matrix that we just worked out. The strain is going to be strain of the X, Y, and shear strain between them. And our U matrix is, or sorry, U vector, displacement vector is what we were given up here. We just put that in there. And we multiply these out. So again, you multiply the top row by this column, and we get that, which is the strain in the X direction. We multiply the middle row by this column, and we get that, which is the strain in the Y direction. And in this case, we multiply the bottom row by the column again, and we get 0. So there's no shear strain in this one. So strain in the X direction is 71.4 by 10 to the minus 6. Strain in the Y direction is minus 42 by 10 to the minus 6. Again, if we take a look at what's going on in this element, that means we have a positive strain in the X direction and a negative strain in the Y direction. So in other words, this triangle will flatten a little bit, okay? It won't be as tall after what's happened, and it'll have stretched that way. And if you look at the displacements given, that makes an awful lot of sense. And again, an important thing to notice, it's a constant strain triangle. So that means even though we have different displacements of each of the nodes, there will only be one strain in the triangle. So in this case, it's got an X, a Y, and a shear. The shear in this case is 0. But that's for the entire element. So strain doesn't vary going through the element. That's why it's called a constant strain triangle. Given that we were told the element was used in a plane stress analysis, we can now work out stress if we want as well. So stress is going to be equal to the D matrix times strain. So the D matrix is the plane stress one. We just fill in all the values. Strain, we've just worked that out. We multiply those by each other, and we find out that the stress is 12 megapascals in the X direction, minus 5 megapascals in the Y direction. So again, given that the element is getting longer in the horizontal and is getting shorter in the vertical direction, those stresses would make sense as well. Okay, so let's go on then to evaluating the K matrix. In one of the previous lectures, we defined strain energy. Strain energy being, half the integration of the volume of stress times strain. We've already just worked out in the previous example there, well, strain is going to be B times U, so we can replace strain with that, and stress is going to be equal to D times B times U. So again, this is our usual method here. And in terms of dV here, we've got a two-dimensional element, so we can replace that with dA and multiply by thickness, which would be constant throughout the element. So again, assuming the thickness in the element T is constant, and knowing that all terms in the B and D matrices are constants, we can rewrite that equation then as half U B dB T integration across the element of dA times U. And then, given that integration dA is effectively the area of the element, we can rewrite that equation again then as the strain energy in the element will be half U transpose TA B transpose dBU. So again, we have these transpose of these matrices in order to multiply them by each other. Okay, so we'll get into that when we look at an example in a few minutes. So comparing this to the general form of the strain energy for an arbitrary finite element, which says that, well, strain energy is going to be a half U K times U. So if we look here, we've got a half U transpose, there's a half U transpose, we've got U at the end, there's U at the end, and then we've got all this bit in the middle here, TA B transpose dB, well, that's going to be K. Okay, so that's where we find out K. So K is going to be TA B transpose dB. So once we know the B matrix, we know the D matrix, we know the area of the element, we know the thickness of the element, we can form the stiffness matrix for the element. So the next thing we need to talk about is dealing with forces. So we can have a body force applied to the element. So remember, a body force is normally something like gravity or some kind of inertia force which acts on every molecule of the body. And that body force can only be resolved into components Fxb and Fyb. So there's the X and Y direction. So again, it doesn't matter what direction the body force is acting on, it will be resolved into X and Y directions. So a typical example, if you're looking at gravity and you had your model set up so gravity was acting in the Y direction, then Fxb will be 0 and Fyb will be just gravity acting downwards. So it acts over the entire volume of the element, but it must be distributed to act on all three nodes. So in FEA, we sometimes want to apply a load to an element or to an edge of an element, But the only way FEA can deal with loads is if they're applied to the nodes. So we must find some way of distributing a load that's applied to an element or an edge onto the nodes. So the distribution comes from the shape functions. Okay, so I'm not going to go through the derivation of this or where it comes from. It's relatively simple, but effectively we have the shape functions act on the body force that's applied. And in this case, it ends up that we apply the body force in the in the y and the x directions, and that is divided by 3 and multiplied by the thickness and the area of the element. Okay, so we have this TA over 3, and here we have the fxb and fxy applied to all 3 nodes, so it's divided by 3. So 1/3 is applied to each node, and it's multiplied by TA. Similarly with surface loads, a surface load acts as a distributed load along the edge of an element, and it can be resolved into surface loads acting in the x and y directions, which are fxs and fys, and these are distributed to the nodes along the edge via this equation here, which is the thickness times the length of the edge over which they act, and divided by 2. So again, if you have a surface load acting on an edge, it's divided by 2 first of all, it's multiplied by the thickness, and it's also multiplied by the length over which it acts. So that distributes the surface loads onto 2 nodes. So here, the body force is distributed onto all 3 nodes of the element. Surface load is distributed onto the 2 nodes which make up the line on which that surface acts. Okay, so let's just look at a worked example to bring some of that together. Okay, so here we're told we have a thin plate. It's rigidly clamped on its left-hand side, so this side here can't move. The bottom right corner is simply supported. So over here, this corner is not allowed to move up and down, but it is allowed to move left and right. There's various loads. So we've got a 1 kilonewton load here and here. We've got a 10 kilonewton load acting down there. We're told the plate is 0.1 meters wide and it's 0.05 meters high. We're told the plate is 0.01 meters thick and it's made from steel with a Young's modulus of 210 gigapascals and a Poisson's ratio of 0.25. So we're asked to use 2 constant strain triangle elements to perform an FEA in a plate. We may assume plane stress, and we're asked in particular to determine the displacement of each of the corners in the plate and the distribution of stress in the plate. Okay, so first of all, we have to decide how we're going to divide this up. So what I've chosen to do is build this FE model of the plate. So there's 2 elements and there's 4 nodes and they're numbered anti-clockwise. So let's just take a look at this. So I've divided the plate here along this diagonal, and element 1 is here, element 2 is there. I've called that node 1, node 2, node 3 and node 4, and I've given the coordinates of each of the nodes. Okay, so we were told it was 0.1 wide and it was 0.05 high, so they go into the coordinates. We've got a load on this node, a load on that node. This node's held, that node's held. This node is allowed to move left and right, but not up and down. So they're the loads and boundary conditions. We're asked to perform a plane stress analysis. So let's maybe just get that out of the way first of all. So let's just calculate the D matrix because it's going to be the same for both elements. So the D matrix in this case, I just plug in the values I was given. So the elastic modulus or Young's modulus was 210 gigapascals, Poisson's ratio was 0.25. Putting all those in here gives me this, and I can simplify that a little bit to make it look like this. Okay, so I've got 56 by 10 to the power 9, 4, 1, 1, 4, and 1.5 down here. So that's my D matrix ready for later on, okay, when I want to form my stiffness matrix. Let's consider the first element, and let's calculate the B matrix, which together with the D matrix would give us K. Okay, so here is our first element. So we've got node 1, node 2, and node 3, and I've chosen to give them the local node numbering I, J, and K. So their global node number is 1, 2, 3, local is I, J, and K, and here's the coordinates of each of those nodes as well. So that gives me, that's my xi, yi, xj, yj, xk, yk. So this makes it really easy then when I have to work out things. So det j, by putting in all the values, is 0.05 meters squared. Again, maybe go and check that that's twice the area of the element. So what's the area of an element? Half the base by the perpendicular height. You'll find that that works out to be twice the det j. The B matrix then is formed by putting all our values in. So there's det j up there. There is various coordinates put in here. So again, if I divide my det j in there, you'll find I get, it makes nice and convenient numbers here, 10 and 20 minus 10 and 20. So there's my B matrix for element number 1. Now we've got to calculate the K matrix. Okay, so we know D, we know B, we know the thickness, we know the area. So let's go through this. So the first thing we have is this B transpose times D. Let's just do that bit first. Okay, so B transpose means I change the rows and the columns of B. Okay, so remember B was a, let's just go back and take a quick look at B here. So B is a 6 by 3 matrix. Okay, sorry, it's a 3 by 6 matrix. It's got 3 rows and 6 columns. Okay, so my first column here, minus 10, 0, 10, 0, 0. In the transpose, I change it around, so it's a 6 by 3. And there's my first row turned into the first column, second row turned into the second column, and so on. So now I've got my 6 by 3 multiplied by my D matrix, which is a 3 by 3. So if you multiply a 6 by 3 by a 3 by 3, you get a 6 by 3. So again, here's my 6 by 3 matrix. So again, I've just highlighted that in red there, because now what I'm going to do is I'm going to say, well, I want that B transpose times D multiplied by B. So I'm going to put a bracket around that and say, well, that multiplied by B. Okay, so I'm going to take that down there and multiply it by my original B. So now I have a 6 by 3 multiplied by a 3 by 6. That's going to give me a 6 by 6 matrix. So that ends up giving me these values here. Okay, so that's my BDB calculated. And now remember K is equal to TA BDB. So it's going to be 0.01, which is the thickness, 0.0025, which is the area, times BDB. So when I do that, I end up getting my stiffness matrix for element number 1. And what I've done here is I've just put on the degrees of freedom across the top and down the side. That's going to make it easier to assemble my global stiffness matrix. So again, the first column and first row are the U1 degree of freedom. The second column and second row are the V1 degree of freedom, and so on. So I've got U1, V1, U2, V2, U3, V3. And again, that comes back to the numbering of the nodes and the way I've numbered them. They just happen to work out like this. You know, it could be I had U3 at the start and, you know, U1 second, depending on what way I numbered it. So I've just numbered it like this and it's worked out like this. So we'll see that the next element is a little bit different. So now let's just go through the same procedure for the next element. In this case, I have I, J, K here, and that means that the global numbering is going to be 1, 3, 4. Okay, so I'm always picking an anti-clockwise numbering scheme, which is kind of the convention. Okay, so I didn't go 1, 2, 3. I went 1, 2, 3. So I, J, K is going in an anti-clockwise direction. Okay, there's the various coordinates. I follow exactly the same procedure. Det J is 0.0005. The B matrix works out to be this. Similarly, B transpose times D gives me the green matrix here. That multiplied by B again gives me my BDB. And then again, putting in the thickness and the cross-sectional area in here gives me my K matrix for element number 2. And again, the last time I had U1, V1, U2, V2, U3, V3. This time, element number 2 does not connect to node number 2, so there's no U2 and V2 in here. Okay, so I've got U1, V1, U3, V3, U4, V4, and the same down here as well. So this element does not link these degrees of freedom to the number 2 degrees of freedom. So now what I have to do is I have to take K1 and K2 and put them together. Okay, so if you look, for example, here, I've got a 6 on the U1 and U1 here. And now in the next slide, that's the contribution there. So U1 and U1 appears in both elements. So there's a 4 from element number 1 and a 6 from element number 2. Whereas if we take something like U2, U1, okay, so node 2 is only in the first element, so there's only one contribution from that. And similarly, if you look at the 4 column and rows, that's only in element number 2, so there's no interaction between element 1 and 2 there. So all these interaction ones where you see a plus is where there's a contribution from element number 1 and element number 2. Okay, so again, let's just again take a look at 4 and 6 here. So why is that there? If I go back to element number 1, there's a 4 in that position from element number 1. And then if I go to element number 2, there's a 6 in that position from element number 2. So there's a contribution from both. Okay, so again, and the ones with the slash here means there's no contribution from either element. Okay, so there's nothing linking there's no element that links node 2 and node 4. So node 2 and node 4 don't occur in the same element, so there's nothing there. Okay, so I can put zeros in there. So in the next slide here, you can see I've put zeros where there were slashes, and I've had, instead of 6 plus 4, I've added together to give me 10. So now I can form my global equation, K times U is equal to F. So there's my K matrix that I've just worked out. There's my displacement vector, and there's my force vector. So now what I have to do is I have to start filling in these guys. So if I look at my problem here, you can see that node 1 can't move, so that U1 and V1 will go to be 0. Node 2 can't move in the y direction, so V2 will go to 0. Node 3 is free to move in both, so I just leave them as U3 and V3, that's what I'm trying to find out. Node 4 will have a 0 and a 0 because that can't move either. And then these loads, I'll have a x direction load on node 2, so that's that one there. I'll have an x direction load on node 3, and I'll have a y direction load on node 3, and then these will be zeros. All the other ones will be zeros. Okay, so eliminating boundary conditions, we see, as I just went through there, U1, V1, U1, V1, V2, U4, and V4 will all be 0. And again, similarly, fx2 and fx3 will be 1,000, and fy3 will be minus 10,000. So that's going in the negative direction. They're going in the positive x. That's going in the negative y. Okay. So now what I'm going to do is put these in here. Okay. So I'm going to apply the boundary conditions and apply the loads. And here is my global equation. So there's my stiffness matrix. There is my displacement vector. With anything that has a constraint on it goes to 0. Here, anything that has a force on it, the force is entered. Anything that doesn't have a force just has a 0. So now what I can do is I can eliminate trivial rows and columns here. So for example, if you look at the first row multiplied by the here, if I multiply this row by that, it says I get 0. So basically, if I multiply something by 0, I get 0. That's a trivial line, so I can get rid of that. But it also means I have to get rid of the column as well, because that's the way matrix algebra works. Again, I can get rid of the second row and column as well, because I have something by 0 is 0. Then I can get rid of this one here. That's also something by 0, 0, and I can get rid of the bottom two as well, because we have the same thing. Something multiplied by 0 gives me 0. So I'm left with 3 non-trivial rows and columns. Okay, so I'm just going to take them out by themselves and write them like this. So now I have a 3 by 3 matrix. I have 3 unknowns that I want to solve for. I want to find out what U2, U3, and V3 are. So solving that then gives me U2 is 3.17 by 10 to the minus 6, U3 is 2.62 by 10 to the minus 6, and V3 is minus 4.44 by 10 to the minus 6. So node 2 has moved in the positive x, node 3 has moved in the positive x, and it has moved in the negative y. Okay, so if I form my nodal displacement vector now, you will see here is my nodal displacement vector with all the known values that I've just calculated filled in. Now that we've determined the nodal displacement vector from the last slide, we can go ahead now and work out the strain and stress in each of the elements. So we can work out strain from B times U, where B is the strain displacement matrix and U is the nodal displacement vector that we just calculated. And then so once we have the strain, we can multiply that by the D matrix to obtain stress. So let's take a look at that. So I start off with element number 1. So element number 1, we're going to use the strain displacement matrix that we previously calculated for element number 1, and we're going to multiply that by the nodal displacement vector for element number 1. So that's going to take the degrees of freedom of node 1, 2, and 3. So the top 6 rows of the nodal displacement vector. We multiply all that out and we get our strain here. We get 31.7 in the x direction, minus 88 in the y direction, and minus 11 by 10 to the minus 6 in the shear direction. So then we can take that result and multiply that by the D matrix, okay, which we previously calculated, and we multiply those out together. We find out that the stress in the x direction is 2.12 megapascals. It's minus 18 megapascals in the y direction, and the shear stress between the two of them is minus 0.92. So we can then go ahead and do the same thing for the other element. So again, the two differences here. The B matrix is going to be different because it's different for element number 2, and also the displacement vector, the element displacement vector, in this case, element number 2 links nodes 1, 3, and 4. So we're going to take the top 2 rows, we're going to skip the next 2 rows, and we're going to take the bottom 4 rows as well. Okay, so it's important we select the right ones here. So when we do that and multiply that out, then in this case we get the stress is 5.86 in the x direction, 1.4 in the y direction, and minus 3.73 in shear stress between the two directions. So here I've just put a summary of all the results on this page. So we have our nodal displacement vector here, our global nodal displacement vector giving the displacement of each node. So the important ones here is this node has moved 3.17 in the x direction, and this node has moved 2.6 in the x and minus 4.4 in the y. And there's our stresses in each of the elements too. So what I'm now going to do is I'm going to jump over to ANSYS Workbench, where I've built an equivalent finite element model of this, using two constant strain triangles, using the same dimensions and everything, same load, same boundary conditions. So let's go and take a quick look at that and see how our results in ANSYS Workbench compare to these results that we have just obtained here. So here I am in ANSYS Workbench, and I've just made a rectangle according to the dimensions that we were given. I gave this rectangle a material properties according to the properties that we were given. And then I set up a mesh. So I divided my model into two constant strain triangle elements. How I did this was in the default meshing properties, I gave ensured that it was linear here and not quadratic. So that meant it had to use linear elements, not elements with straight sides and just corner nodes. And then when I went into the mesh, I assigned a face meshing on this, where I told it that I wanted it to use triangles. And then I performed an edge sizing in each of the edges, and I told it I wanted only one element division on each side. And it's very important then that I went in and selected the hard option here, because by doing that it forces Workbench to stick to what I've told it to do, because otherwise Workbench would attempt to do a better mesh because it's trying to help me out, and it would try and override what I did and maybe use more elements in here, which would be the sensible thing to do in this case. So I want to override that, so I've put in the hard. So in that case I end up with my two elements exactly the same as we just had in the problem that we did by hand there. So let's take a look at the loads and boundary conditions. So first of all, we have a fixed support on those two nodes there. So they're held in all degrees of freedom. But a frictionless support on the bottom face here. So that means that this node here is free to move left and right, but it can't move up and down. I've put a force up in this corner here, which is 1000 in the x direction and minus 10,000 in the y direction, which is the same as the problem that we just looked at. And finally, I have a force down here, which is 1000 in the x direction. So we solve that then, and let's take a look at some of the results that we obtained. So first of all, let's look at the x direction deformation. So here's our, obviously this is exaggerated, so you can see here it's scaled up quite a bit. Okay, so you wouldn't actually see this type of deformation because it's 3 by 10 to the minus 6 meters. It wouldn't be visible, so we've scaled it up to exaggerate it a little bit. And what I've done here is I've taken a probe and I've put a probe on the two nodes. Okay, so down here I've got an x direction deformation of 3.16, which compares very well to the 3.17 that we just worked out. And up here I have an x direction deformation of 2.61, which compares to the 2.62 that we just worked out in the hand calculations. Let's have a look at the y direction. So obviously this one can't move in y, so here I've got minus 4.4 by 10 to the minus 6, which is exactly what we got in the hand calculations. Let's take a look at the stresses. So again, I've put a probe in here, but you'll see that there's, as the name implies, with the constant strain triangle, it means there's only one value of strain and stress in the entire element. So even though we can have different deformation at the nodes, we're only going to get one value of stress or strain. So I've just turned on the probe here, and it allows me to move around the element. You'll see it's unchanging inside the element, and again it's unchanging inside here as well. Okay, so this is our x direction stress. So we already calculated that there should be 2.12. I've got 2.13 here, and for element number 2 we've calculated it's 5.86, which is exactly what I've gotten here. So let's move on to the normal stress, or sorry, the stress in the y direction. So again we have minus 1.8 e to the 7, which compares to the 1.81 that we obtained in our hand calcs. And up here we've got 1.46, which is exactly the same as we had in our calculations. Finally then the shear stress, minus 9.33, It compares to 9.2, and 3.73 compares to 3.73. So you can see that we got pretty much exactly the same results in our workbench model as we did in our hand calculation model. So again, there's a summary of the results that we obtained, and they line up very, very well with the results that we obtained from Workbench. Before we move on from this example, let's just take a look at one more thing. So we're still using the same example, the same two elements. We've already got our results from our finite element analysis here, but now we're going to look at something different. We're going to say, well, what's the displacement of the point P? The point P is at the coordinates 0.075, 0.025, so it's in here somewhere inside in this element. So it's not on a node, it's at a different point that's not represented by one of the nodes. This is just to illustrate why we use our shape functions to interpolate displacement within elements. So P is in element 1, it's in here. And first thing we need to do is we need to determine the natural coordinates of the point P in order to determine the displacement of the point P. So we're going to use our iso-parametric equations again, and we're going to use the one that relate eta and neta to x and y. And we're going to start off with the x version here first. And we're going to put on the known values in here. So remember, xi is the coordinate of node I, which in this case will be 0. xk is the coordinate of node k, which in this case will be 0.1. And again, xj is going to be 0.1 as well. So we put those values in and we get this equation here. Then we can simplify the equation and simplify further, end up here, and we end up finding that eta is equal to 0.125. So that's the eta coordinate of the point P, the x coordinate 0.075. Now we need to do the same with the y coordinate and find its neta coordinate. So again, we use the y version of the iso-parametric equation, and again put in all our known values. Simplify the equation, keep on simplifying as much as we can. We end up here having, well, 0.5 is equal to eta plus neta. We already know what eta is from over here, and we can put that in and we find out, well, neta of the point P is 0.375. So the x and y coordinates of the point P are that, and the eta and neta coordinates of the point P are that. So now that we know that the point P has the natural coordinates eta and neta as follows, what we can do is we can construct the shape function. So remember, Si is just eta, Sj is neta, and Sk is 1 minus eta minus neta. So there's our three shape functions at the point P. So we've worked out the shape functions at the point P. Now that we know the shape functions at the point P, we can use our usual equation that says, well, displacement of that point is equal to S times U, and S is the shape function matrix. So we put in our Si, Sj, and Sk in there. And U is the nodal displacement vector. In other words, it's the list of the displacement of each node, which we have here from solving our FEA. So we know S and we know U, and we can multiply them together. And when we do that, we end up getting the x direction displacement of the point P, or the U displacement, is 2.3, and the V displacement, or y direction, is minus 2.22. So again, it's always worth checking, do these make sense? So if we look here, what does our nodal displacement vector tell us? Well, it tells us that node 1 did not move at all. Node 2 moved 3.17 in the x, and node 3 moved 2.26. So we've been told that our point P, which is in here somewhere, has moved 2.3. Okay, so it's less than 3.17 here, and slightly more than that, which makes sense because this kind of ends up coming out like that, if you remember from when we looked at Workbench a minute ago. So it makes sense that a point here is going to move out here a bit. And again, the V direction, or the Y direction displacement, is minus 2.22 by 10 to the minus 6. And the y direction displacement of this node is minus 4.44. So this one is going down 4.44. It would make sense that a point in here would go down about 2.22. So those results would appear to make sense. Okay, the final thing we're going to do then is just look at some of the limitations of the constant strain triangle. And to do this, we're going to reference case study C in the book. So what case study C does is it performs a beam bending analysis, and it looks at using different types of elements to do that. So it uses one beam element, It uses 16 constant strain triangle elements. It uses 16 linear strain triangle elements, which are quadratic triangles with mid-side nodes. It uses 8 Q4 elements, which are 4-node rectangular elements. And it uses 8 Q8 elements, which are 8-node curved edge quadratic rectangular elements. And what we do is we get a table like this in the case study where we do the analytical solution for beam bending. So there's forces given and there's cross-sectional areas and so on given in the example. So the analytical solution to the given parameters is that we get a deflection of 0.768 and a stress of 4.8 megapascals. So by using one beam element, we get very, very close straight away. So we get 99-100% accuracy in terms of deflection and stress by using one beam element. Now, interesting, let's look at what this model here, consisting of 16 constant strain triangle elements, gives us. So we get a deflection of 0.089 millimeters compared to 0.768. So that's 11% of the target, and we get a stress of 0.5, which is 10% of the target. So clearly that's very, very poor. So the constant strain triangle, at this number of elements does not give a very good result. If you compare that, for example, to the Q4 element, which is we've only got 8 of those, so less than we have of constant strain triangles, we actually get a 96% accuracy in terms of deflection and an 87% accuracy in terms of stress. And then even better again, the Q8 elements here, the 8-node quadrilaterals, with only 8 of those, we get a 99 and 98% accuracy. So, the obvious question, or the obvious route here, would be to have more of the constant strain triangles and see how much of those we need to get closer to our analytical result. And this is basically known as a mesh convergence study. So in this case, it was found that we needed 256 constant strain triangle elements, and at that stage we were still only at 88% accuracy in terms of deflection and 92% accuracy in terms of stress. So clearly there's a big problem with the constant strain triangle there, in that because it has an inherent inability to accurately model varying strain or stress fields within a single element, it proves to be quite inaccurate, and we need to use lots of them to try and model rapidly changing strain or stress fields. So there's a very slow convergence with constant strain triangle elements, whereas if you look at, for example, the linear strain triangle, going from 16 to 64 of them, we went from 98, 93 to 99, 98%, and the Q8s, for example, we only need 8 of those. The Q4, is a bit behind the constant strain triangle, but not as bad. But the Q8s, only 8 of those gave us a straight away 99% accurate result. Another well-known problem then with the constant strain triangle is if we try and use it to model something like this, where we've got pure bending. So here again we've got a beam, and it's represented by 10 constant strain triangle elements. So here's one element, there's another one, and so on. And we have these nodes here fixed in all degrees of freedom, and we have pure bending here. So in other words, we've told this node has a force acting this way and this node has a force acting that way, so we've just created a bending moment. The neutral axis of the beam is the x-axis here. So what would we expect if we plotted stress along this neutral axis? Well, because it's the neutral axis, we'd expect nothing. We'd expect to get a 0 stress all the way along the neutral axis. What actually happens is, in this case though, if we plot stress using these constant strain triangle elements, we're going to get something like this. We're going to get this square wave pattern here. And the reason that occurs is if we look at what's going to happen here. So first of all, because we have a positive load here and a negative load here, or a tensile load and a compressive load here, what's going to happen is our beam is going to bend downwards. Okay, so this is compressed, this is the compressive edge, this is the tensile edge, so it's almost like our beam is going to bend down. So if we look here at what's happening with this element, the majority of this element is down here. And remember, it can only have one strain, which means one stress. So because the majority of this element is on this side, the majority of the area of this element is going to be in compression. Okay, so we're going to get a compressive stress until we move to this point here, and at which point it's going to abruptly change to being tensile. Okay, so that's what's happening here. We're getting compression here, abrupt change to tension, an abrupt change down to compression again. So think about it as we move along here. We're compressive in this element. This element is going to be tensile. This element is going to be compressive, and so on. So we get this square wave pattern happening here, which is obviously not what is supposed to happen. We're supposed to get a zero stress along the neutral axis. So our constant strain triangle element is very bad at modeling bending. It is very inaccurate in high stress gradient regions. So when stress and strain are changing rapidly, your stress concentrations or sharp corners or holes, we're going to need a lot more constant strain triangle elements than we would need of the other elements we looked at there, the Q4, the Q8 elements. The constant strain triangle elements are also very slow to converge, and there's other more specific problems with them as well. So they're very difficult. They find it very difficult to model nearly incompressible materials where Poisson's ratio is approaching 0.5. So things like rubbers, hyperelastic materials, they find it very difficult to do that. And also we get a thing known as shear locking during bending as well. So it's it's down to the stiffness in bending problems. Because we assume a constant strain within the element, we can't represent the complex strain gradient that occurs where we have a change in strain in the x direction when we have strain in y direction and vice versa. And this results in these artificial shear stresses, or shear strains or shear stresses being created, which absorb excess energy, and it makes the model less flexible than it would be in real life. So they're the main problems with the constant strain triangle. Why are they still used? Because mainly for the purpose that we used it in this video, it's the most simplest element to explain in 2D, and if you can understand the constant strain triangle, then we can build on that, and we can look at the Q4 element and the 6-node triangle and the 8-node rectangle as well, which is what we're going to do in the following videos. So it's always used more from an academic perspective to explain two-dimensional elements, because if you can kind of get your head around the constant strain triangle, it's easier to get your head around the other ones. Okay, so just to finish up then, we'll just take a review of what we did in this video. So we looked at plane elements in general. We looked at plane stress and plane strain and establishing the D matrix. So the D matrix, remember, relates stress to strain. It's often known as the material property matrix, and it's used in the construction of the stiffness matrix. We defined what the constant strain triangle was. We talked about iso-parametric mapping, which is very important, which we're going to use for all the other 2D elements we look at from now on. We introduced the jacobian matrix, which again is a very important part of the mapping process. We use the jacobian to form the B matrix, the strain-displacement matrix, which then is subsequently used to form the stiffness matrix. So we use the B and the D matrix to form the stiffness matrix. We just talked about distributing body forces and surface forces onto the nodes using the shape functions. We looked at a number of worked examples, and then finally we just talked about the issues with the constant strain triangle and some of the limitations on its use. So that's the end of our video on the constant strain triangle. So again, remember, this material is taken from my book, Practical Stress Analysis with Finite Elements. If you want a more detailed explanation, please do go ahead and buy the book, and there's a link in the description for where you can buy it.